Okay, so let us continue our second section on generative modeling. And actually, please look at some announcements in Telegram. So after this session, so please stay here. So we will have joint photo. So for this photo, we also need our colleagues from computer vision section. So they will join us here, and the photo will be here on the stage. And after that, we go to atrium of HEC University. So it is another building. So if you're not from HEC, so please follow video, or we can meet here on the second floor, and then go together to atrium. I think it will take us maybe at most 5 minutes to go there. Okay, so so we continue, and our next first speaker for this section will be Ildus. Ildus, where are you? Okay, Ildus here. So please go. So presentation, I hope, will appear. So. Yeah, okay. So do you have microphone?
The microphone. Can you hear me, actually?
Yes, we can hear you. Thank you.
Yes, and the clicker also works. So, okay, let us start, I suppose. So, Alexei told us to stay here in this beautiful hall, but actually, do we even need to stay, or do we need not to stay? So this is what is about our paper. So I would like to present you our latest new RIPS paper. Actually, this one is very fresh, and you have a unique opportunity to hear it the first time, because we submitted the final version, I think, just an hour ago. So yeah, you're please listen carefully so that you can, I don't know, maybe give some corrections for future presentations. So here we try to understand how to construct effective ensembles when we're talking about the transfer learning setup, and this is what about our paper, and so what are the problems when we are trying to ensemble the networks in the transfer learning setup. So let us start with a brief background. Actually, as I already told, we are working in the transfer learning setup. This is a scenario where the training of the neural network consists of two stages. So first of all, you take a kind of a large general data set, for example, ImageNet, and pre-train your model to this large general data set. Then you want to do the knowledge transfer to smaller data sets, and in this case, you take your target smaller downstream data set, for example, CFR10, and fine-tune the model to show strong quality on this data set. So we'll actually want to combine it with ensembling, a quite common technique where you take several models and average their predictions to get more to get the predictions of more quality, or sometimes even more robust predictions. Today, I think everyone is quite crazy about large models in vision and both in text applications. But in fact, when you want your model to have good performance on real-world tasks, you want it to be robust, and you want to do the uncertainty estimation of the predictions. So I think this is really important sometimes to use the ensembles, because they allow you to improve the quality of the models and, moreover, to do the uncertainty estimation. So when we are talking about the transfer learning setup, there are several ways to construct deep ensembles of neural networks. So for the ones not familiar, this sketch is a sketch of the loss landscape, and these lines, they show the level lines of the loss function over the weight space. And so there are two options how to construct deep ensembles of neural networks in this setup. So the first one is a local deep ensemble, where you have only one pre-trained model, and then you do several independent stages of fine-tuning of this model. The resulting models are located in the same so-called low-loss basing, and actually, because they're live in the same region of the loss space, the models are quite similar, but when we construct ensembles, we want the models to be as diverse as possible. So actually, the quality of such ensemble is not very high. Another option is to take several pre-trained models, which are pre-trained independently from each other, and then fine-tune each of the model to the target task. And in fact, the models which we obtain in this scenario will be located in different basins, which means that they will be more diverse, and thus will form a better ensemble. But the main problem with the global deep ensemble is that we actually don't have so much resources to train several pre-trained checkpoints, because usually pre-training is much more resource consuming than the fine-tuning. So the main question we're trying to answer in our paper is to understand, is it somehow possible to create a strong ensemble which performs good on the target dataset when you have only one pre-trained model? So to do so, we use some more advanced ensembling techniques. Actually, we consider the methods with cyclical learning rate, and they are quite popular in the regular non-transfer setup. So one of these methods is snapshot ensemble, and the idea is to use the cyclical learning rate and to take the models at the minimum of the learning rate. So the motivation behind this method is to allow our optimization to jump over different low-loss basins, and thus we will pick the models which are quite diverse to each other. So here in our paper, we call the behavior when the models of the ensemble are located in the same basin local behavior, and the scenario where the models are taken from different low-loss basin semi-local behavior. So in this scheme, you can see the semi-local behavior where the optimization jumps to different low-loss basins. So a few details about our experimental setup. Most of our experiments are done on the ResNet 50 architecture. We do the pre-training on the ImageNet dataset, actually with two possible ways, supervised and self-supervised. And we consider three different downstream image classification datasets, which are two variants of the CFR dataset and the Sun database. Actually, in our final version, we have more extended experimental setup. So I think in a month or so, the final version will appear in the open access, and you'll be able to see the results yourself. So here are results for the snapshot ensembles. These figures show the quality, the test accuracy of the ensembles of different size. And first of all, you can see the baseline lines in this plot, which are black and gray and correspond to global and local deep ensembles. And indeed, there is a quality gap between them. So you can see that for both types of pre-training, we have global ensembles being superior to the local ones. Moreover, we consider different hyperparameters of the snapshot ensemble cycles. These are the maximal learning rate of each cycle and the length of the cycle, which is measured in the number of epochs. So these colorful lines for the snapshot ensembles, they're actually the hyperparameters, which are the multiples of the optimal ones for fine-tuning a single model of a local deep ensemble. So in fact, we can say that for supervised pre-training, we see that snapshot ensembles are able to outperform local deep ensembles. However, when we switch to self-supervised pre-training, we see that they're clearly losing to the local deep ensemble when we increase the size of the ensemble to the maximal size of 5. So actually, what is more interesting here, we can see several types of behavior when varying these hyperparameters. So the first behavior is called more local. This corresponds to the smallest values of the hyperparameter, both the learning rate or the number of epochs. And because of the smaller learning rates, the models don't have an ability to go too far away from each other. So they became quite similar, not diverse enough, and this results to the slowly growing quality of the ensemble. So when we increase the values of the hyperparameters, we get better results, which we call optimal regime. And finally, when the values of the learning rate of the number of epochs are too high, we see that the ensemble starts to degrade after some point. So we conducted some additional analysis to understand why this situation actually happens. So here on this slide, you can see the analysis. On the left part of the slide, there is the accuracy of individual models in the ensemble. And on the right part of the slide, there is the interpolation between the weights in the ensemble, which actually indicates us how the loss landscape between these models looks like. So it's easy to see here that the quality of individual models starts to degrade after each consecutive cycle. Moreover, this degradation is the most significant for the more semi-local experiment, which actually meets with the right part of the slide, where you can see that actually the models of the semi-local experiment are located in different low-loss basins, because on the segment connecting the first and the last models, there is a drop of accuracy in the middle. So the optimization went to a different low-loss basin. So here we conclude that these type of methods with cyclical learning rate, which use sequential cycles of the learning rate, they are not efficient in the transfer learning setup, because we clearly can see that there is a degradation of quality of individual models, which is related that we're going too far away from the pre-trained checkpoint, we'll lose the advantages of transfer learning, and our models start to overfit to the trained set of the target data set. So we tried to fix this and proposed our own modification of the snapshot ensembles, which is called star SSE, because it actually does the training not in sequential, but rather than in parallel style. So we've fine-tuned the first model as is done in regular SSE, but then we launch parallel cycles of the learning rate, which do not allow us to go too far away from the pre-trained checkpoint to not to lose the advantages of transfer learning. So this is how it looks like on the scheme of the loss landscape. And here are the results. So besides considering the ensembles, we also consider so-called model soups. Actually, they are quite similar to the ensembles, but in ensembles, you actually average the predictions of the models, but in model soups, you average the weights. So quite similar to stochastic weight averaging, if anyone is aware of it. So on the top line, on the top half, you can see the in-distribution accuracy measured on CFAR 100 dataset. And on the bottom line, the result of distribution accuracy on the corrupted version of this dataset. So when we're talking about in-distribution accuracy of the ensembles, we can see that star SSE, the optimal star SSE experiment, outperforms both SSE and the local deep ensemble, which is actually what we wanted to do originally. When we consider the out of distribution, the results are they are not as good actually, because we can see that the quality is lower than for the local deep ensemble. However, when we consider the weight averaging instead of the prediction averaging, which is a model soup, we can see that the optimal star SSE experiment performs well on both in distribution and out of distribution data. So to finalize, first of all, we show that the methods with sequential cycles of learning rate, which are popular in non-transfer setup, they are not very good for the transfer learning setup, because after each cycle, each consecutive model becomes worse and worse, and if the hyperparameters of the cycles are too high, you go out of the initial low-loss basing, which leads even to more significant degradation of the models. So based on this analysis, we propose star SSE, which is similar to the original method, but it uses parallel cycles instead of the sequential, and we show that it outperforms both SSE and local. Actually, here I showed the results only for CFAR 100 dataset, but the results for other datasets will be on the poster. And besides effective ensembles, we can also do effective weight averaging, which helps us to show strong performance on the out-of-distribution data. So I think that's it. Ready for your questions.
So please, questions? Yes.
Thanks for the talk. So I think this ensembling technique was introduced in was landscape paper by Garipov, Wilson, and Vetrov, when I think they also used cyclical learning rates and found out the minima separated with loss barriers. And my question is whether one can somehow evaluate that overfitting issue in transfer learning via some regularization, like weight decay or L2 distance between features of the original model and the fine-tuned one.
This is actually a very good question. Thank you for you answering it. This is a very interesting direction for research. Actually, when we were writing our paper, I got an email from a colleague from the New York University, I suppose, who asked us to cite their paper, which was about fitting a normal prior for the pre-training. Actually, what they do is they take these pre-trained models and fit a normal prior with the center with these pre-trained models, and then they do their fine-tuning procedure using this prior as a regularization. In fact, this may help to improve the accuracy of distinct models, but it doesn't fix the problem in the sense that it may help only for the local behavior. When we want to traverse to different basins to get more diverse networks, this prior most probably won't work because they are unimodal, they are normal, and thus they don't really help us to understand how the loss landscape looks for different low-loss basins.
Sure, yeah, indeed, because it's only about local behavior and only, I think, up to second order behavior, and these loss basins are indeed something that is not captured by normal approximation of the current optimum.
Yeah, absolutely.
Thanks.
Actually, how did we ask you to cite their paper? We just wrote you have to cite our paper?
No, that wasn't this way, but just explaining. Actually, we somehow overlooked that work, and it's really helped us to position our research a little bit better. So,
Okay.
no negative.
Okay, so some other questions? Yes, please.
Hey, thanks for your talk. So my question is, what is the advantage of using the star SSE over SSE and other ensemble techniques like dip ensembles, right? So in general, for uncertainty quantification, it just seems that that star SSE would give us much precise sort of the uncertainty might be a little bit underestimated, or I might be wrong.
Well, are you asking me about the non-transfer setup or?
Well, in general, so the usage of the ensembles for uncertainty quantification, it's...
well, we don't measure uncertainty in our paper. We focus primarily on accuracy. Actually, we also measure the diversity of models somehow. But this is a little bit different. Actually, we were aiming to do the... I think I'll better show you this slide. In fact, where this is like approximation of what is actually going on. And when we use SSE in the transfer learning setup, the models quite fast go away from this center of the basin, and they have lower quality. And if we want to do the uncertainty estimation, we most probably want to cover the center of the basin, which shows us the best models in terms of test accuracy. And I think when we do the sampling like inside this low loss region, it also helps us to do better uncertainty estimation.
Okay, so the more parallel estimations I do, right? So the more estimates I get, and better is the estimation of uncertainty.
Once again, please.
So the more parallel estimations I do, right? The next step of the star SSE, right? So I've reached, so I have a fine-tuned model, right? So I'm doing the next step of star SSE, right? I have the parallel estimation as far as I understand. So
no, I just want to say that these models are better. They are covering like the region of lower loss, and they are. Well, actually, they have quite similar diversity to the original SSE models. We measured it, and this high level of diversity also would help us to do the uncertainty estimation.
So you've measured, so your results show that there is no significant difference in SSE and star SSE in terms of uncertainty estimation, right?
Again, we didn't do the experiments on uncertainty estimation, so I can't actually say yes or no.
Okay, thanks anyway.
Okay, so if no other questions, so let's thank Ildus again. Ildus, thank you.
Thank you.
And we go to our next speaker. I think Nikita Gushin, yeah? Yeah, should be Nikita Gushin, expert about entropic, no, again. So we had kernel, now we have entropic no-error optimal transport. So section about so we have two sections about this, about no-error, about optimal transport. So we will know everything about it. Okay, so could you please start presentation? So it should be entropic no-error. So we have some technical problems. But just wait. Okay, no,
Not this one.
Not this one. So this
is.
one will be next one.
Not this one again. You spoiled every next presentation.
Like we say feels like it should be intuitive.
And not this one. So there was number 2 in a Google Drive before title of my presentation. Yeah, this one, thank you.
Thank you.
Okay, yeah, again, we will talk about optimal transport, but it is interesting because it relates with diffusion processes. So this, my presentation is about paper which was recently accepted at NeoRIPS 2023. So again, what is an optimal transport? In this problem, we consider 2 probability distribution, P and Q, and we also have some cost function C, which defines metric between 2 objects, X and Y. And we want to find a map T, which will map our distribution P into distribution Q, but it will have the minimum expected value of this cost function. So we just want to map one distribution into another, but we want to preserve content. Okay, so this problem is popular in the field of domain translation, in which we usually think that P is a distribution over some images, and Q is also distribution over images, but in different style. And we want to find a map which will redraw images in different style, but the important moment is that we haven't any pairs. So it is a completely unsupervised problem. And the second important branch of applications is about using to analyze single-cell biological data. It is a very powerful technique, single-cell sequencing, which combined with optimal transport theory allows to answer a question how distant cells interact with some chemicals, for example, with drugs. We can analyze how cancer cells reacts to some various drugs, and we can use it to facilitate our research in developing new drugs. Okay, so, but we will consider the special version of optimal transport. The difference is that we just add one term, which is entropy, and this term is multiplied by epsilon. So by doing it, we slightly change our problem. So now we do not want to find some deterministic map T. We want to find a stochastic map. So I mean, we map object x1 into distribution py given x1. Okay, so also this problem has dynamic version, which is known as a Schrödinger bridge problem, and it was formulated by Erwin Schrödinger. And in this case, we need to find a stochastic process, a stochastic diffusion process, TF. So it is given in the form of stochastic differential equation, where we have function f of x, t, and t. It is a drift function. And also we have differential of Wiener process multiplied by coefficient square root of epsilon, which again will define how diverse our map will be. So again, we will map distribution P0 into distribution P1 with some stochastic process TF. And And the unique property is that solution to this Schrödinger bridge problem is, again, is a solution to initial original entropic optimal transport problem. And why we even need to consider such complex things. So again, Schrödinger bridge problem has even more interesting application in the field of single-cell biological data, because it allows not just find some map between cells before and after interaction with drugs. It allows to find time dynamic of such interaction. And there are even articles in Nature Methods about using such techniques. And in the case of generation and domain translation, this problem is interesting because it allows to find a stochastic diffusion process which has more straighter trajectories. As you may know, today not only we, there are intensive research towards developing new ways how to sample from diffusion processes faster. And solution to this problem it's one of the way to sample from diffusion processes faster. So okay, in our work there is a very tough theoretical background, but in the end we obtained a theorem which allows to reformulate Schrödinger bridge problem as a Maximin problem. So previously we have a constraint problem, but we cannot solve it directly. So now we can solve it because it's given in the Maximin form, and we just need to parameterize this additional function beta and function tf with some neural networks, and then we just can optimize it by using standard stochastic gradient descent algorithm. Okay, so there is an algorithm. There are just two cycles. In inner cycle, we optimize stochastic process. In outer cycle, we optimize function beta. Okay, so we started with a very simple example, as in every new theoretical paper about generation. We just considered a map between input distribution, which is a Gaussian distribution, and a mixture of 8 Gaussian distribution. And we show that, okay, for epsilon 0, we obtained a process which has straight lines. For bigger epsilon, we see that there are more noise in trajectories. Then we, as you know, usually in theoretical works, people generate MNIST, but we went further. We started to generate colored MNIST. We take digit 2 and 3 from this data set, color it in different colors, and we just want to, in paired setting, we just want to find a stochastic diffusion which will map digit 2 into 3. And as you can see, for bigger epsilon, we have more diverse samples. Also, there are trajectories. So for bigger epsilon, we have more noise trajectories. While this setup is very easy, other methods which solve Schrödinger bridge problem cannot do even this, because some of them cannot produce good samples, and some of them solve this problem for such big epsilon at which solution is meaningless. So I mean that the color doesn't preserve for most of samples. Okay, then we consider some simple setup from our competitor. We just want to deblur images. So we have original celeb images and blurred celeb images. We want to solve this, again, problem in unpaired setup, so we haven't any pairs. Okay, so again, our competitor cannot solve this problem because it solves this only for very big epsilon, where solution is meaningless. Our method can solve it. However, for bigger epsilon, due to higher gradient variance, our method start to produce bad samples. Okay, so there are also trajectories. Again, there are more noise in case of bigger epsilon. And also, after doing it, we already wrote a new paper in which we used every theoretical result from from this paper to obtain new solver which is more stable and converge faster. That's all. Thank you for your attention.
Okay, thank you very much. So, questions? Could you please go to one of the first slides with some definitions? Okay, yeah, this one. So what is joint distribution of, so it is called the process TF, attaining the minimum has joint distribution P. What is so joint, what do you mean by joint distribution here?
I mean that so we have some diffusion TF and we can take object X1 and map it by diffusion TF.
Yes.
So, and by doing it many times, we will obtain some distribution Py given X1.
Okay.
And I mean that this distribution for optimal process TF, which is a solution for Schrödinger bridge, this distribution will be the solution for entropic optimal transport. So these two problems are very related, and using background from both of them allows to find new solvers.
Okay. Okay, so any other questions? Yes, you have questions?
You mentioned in the motivation that your results can be used in biology. Why is it beneficial to use entropic optimal transfer in biology while there are other types of optimal transport like we saw today?
Okay, so the important moment is that entropic optimal transport has a dynamic version, which is a Schrödinger bridge, and while usual optimal transport can answer a question what was before, and so we have a cell before interaction with some drugs, and how it will look after interaction in sense of genes which is expressed. While when you have a dynamic formulation, you can also recover dynamic of so you can recover state of cells in intermediate time steps.
Okay, thank you. Some other questions? So if no, so thank you very much. So we go to the next speaker. So next speaker is who is our next speaker? Piotr Makarov, yeah? Okay. So Piotr is going to talk about, so you're going to talk about benchmarks, yes?
Yes.
Okay. So it will be also about Schrödinger, building the bridge of Schrödinger. So a continuous entropic optimal transport benchmark. So I expect that we again start from some definitions of optimal transport.
Yes, we have a clicker.
It will be, I think during...
Yeah, can I start?
Yeah, during dinner it will be main question. I think we will ask, so give definition of optimal transport. Okay, please start, yeah.
Let me start. My name is Piotr Makarov, and now I'm presenting our work, building the bridge of Schrödinger, a continuous entropic optimal transport benchmark, which was accepted to the last NeRIPS. So let me give a brief, one more brief introduction to entropic optimal transport and Schrödinger bridge problems. Well, we have two distributions, P0 and P1, and we want to map from one distribution to the other distribution. And this problem could be formalized, for example, as an entropic optimal transport problem. This problem can be considered as a relaxation of well-known optimal transport problem, where we just look for a map which transform from one distribution to the other, while minimizing the quadratic square norm between the input images, or just points from source domain and target domains. And in entropic optimal transport framework, we add additional entropic regularization, which introduces stochasticity in the maps. So we have one input point, and it can be transformed to the several points from the target domain. And it's really reasonable assumption in a variety of applications. And this diversity could be explicitly controlled by regularization strengths, epsilon. The other closely related, as my colleague has already said, problem to the entropic optimum transport is a Schrödinger bridge problem. In this problem, we also look for a stochastic map from one distribution to the other, but we look for this map in terms of stochastic processes, which starting at the initial points and finishing at the target domain. And why this problem are related? Just because the marginalization of optimal stochastic process on the source domain and target domain yields entropic optimal transport plan. This slide was already shown. Let me briefly repeat it one more time. So why we need to solve these problems? Just because they appear in various applications. We can consider them in various practical applications. For example, for domain translation, where we want to map from one for image to the other image data set while preserving some content. For example, in order to create anime faces of original faces. In this case, we want these anime faces to be similar to the original faces. And the other bunch of applications is single-cell biological data, where we for example, consider the evolution of cell population dynamics. And in this setup also appear a lot of problems which could be formalized as entropic optimal transport or Schrödinger bridge. And such practical demand motivates a lot of studies in the sphere. So there are a lot of EOT and Schrödinger bridge solvers. I don't want to get into details of the solvers, just want to highlight that this problem is of interest in ML community. However, there is one general problem among all of these solvers. Most of them actually lacks any empirical verification as EOT or SB problems. So we don't know how well they actually solve these problems. Why this? What's the reason for this problem? Just because for now, only for trivial Gaussian to Gaussian case, we know ground truth solution in order to compare solvers. And because this motivates our study to propose a generic way for constructing non-trivial and scalable even to image data set of images or even other arbitrary data, benchmark pairs of probability distribution, so source distribution standard distributions with known ground truth, EOT, and SB solutions. The key theorem behind our research is presented here. So it turns out that if we have a distribution P star on not distribution, but on the joint source and target domain. And this distribution, the conditional distributions of target points conditioned on source points, if they satisfy one particular property shown in the slide in the formula, where f is a almost arbitrary scalar-weighted function. So in this case, this P star plan actually EOT plan between the marginals of P star on the source domain and target domain. And the optimal Schrödinger bridge drift, which drives the stochastic diffusion between source and target domains, is also can be expressed. But still there is one problem, because here we know these conditional distributions only up to some constant, which limits the applicability of this formula in, for constructing actual ground truth plans. And in order to solve this problem, we consider specific potentials f. So we have here we have a potential f which appears in the formula, and we pick particular potentials with just log sum exp quadratic potentials. And in this case, the conditional distributions p star y per x permits closed form solutions, and so does optimal drift. So what the main benchmark idea? So how to construct benchmark pairs? So the idea is as follows. We have distribution P0, which can be arbitrary, for example, distribution of images. And we pick any LSE potentials. And we construct the P star distribution just by multiplying conditional distribution by source distribution. And this yields us our desired benchmark pairs. So distribution P0 and P1, which could be easily obtained, at least samples from this distribution could be easily obtained. On this slide, we provide an example how it works in practice. Here we build a benchmark pair depicted on the first column. So yellow points here is source distribution. It's a 16-dimensional space, just a PCA projection. And yellow points depicts target distribution. As you can see, this is multi-marginal distribution. And on the image below, we demonstrate the conditional distribution, so y per x. And also here we demonstrate how different solvers presented in this presentation, which we discuss in this presentation, performs in this setup. This slide demonstrates quantitative comparison of different solvers. So here we just consider different dimensions, and for each of the dimensions we construct benchmark pairs and aggregate the obtained results for different solvers. In the first column, we demonstrate how these solvers actually solve generative modeling tasks, so how they map from the source distribution to the target one. And the second column shows how they actually solve entropic optimum transport or Schrödinger bridge problem. Actually, I don't want to get in details why this or that problem work or doesn't work. I just want to highlight that our benchmark pairs allows to answer the question whether solvers actually solve EOT or SB. And this can be used, for example, for tuning hyperparameters and to understanding what's going on. And in the last slide, I demonstrate that our methodology could be applied even for image data. So here we can see as a P0 distribution, we consider Saleba images. And why it's important? Because the obtained benchmark problem resembles real-world problem. So on the one hand, our constructed benchmark pairs could be considered as a benchmark. On the other hand, they resemble denoising problem. So one distribution is just noisy images, and the other distribution is the clean images. And solving EOT in this case is just denoising. That's why our benchmark pairs really resembles real-world scenarios. So, conclusion. We propose a generic method to construct pairs of distributions with analytically known EOT and SB. And secondly, we evaluate different popular EOT SB solvers on our constructed benchmark pairs and provide a way how to adapt our methodology to data of arbitrary complexity. Thank you for your attention. Now I'm ready to answer your questions.
Okay, thank you very much. So questions? I think now everything is clear about optimal transport. So you're always doing second order optimal transport. So maybe it's time to go beyond second power. I mean, consider optimal transport like power 4, for example? What do you think? Why not?
You mean when you take your metric,
Yeah.
yes, and
Yeah.
well, actually there are methods developed for arbitrarily cost functions.
Yeah, for example.
But constructing benchmark in this case is rather, I guess it's really difficult.
Okay, okay, so if no other questions, so okay, so thank you very much. So we have our next speaker. So next speaker will be Milena, yeah? Okay, yeah. Okay, so it will be extremal domain translation with no optimal transport. Yeah. Okay. Yeah, okay. Yeah, okay. Okay, so Milena, please. Okay.
So, hello everyone, my name is Milena Gazieva. I will talk about yet another optimal transport. This is our paper, Extremal Domain Translation with Neural Optimal Transport, which was recently accepted to the New RIPS conference. So, the task which motivated our study is a widely known domain translation task when the learner is given empirical samples from two different domains, input and target, and needs to learn some translation map, which could be applied to some new samples from the input domain to derive the generated samples from the target one. This task spans a variety of popular computer vision problems. For example, it is image super resolution, style translation, and others like image learing, and so on and so on. So, very important problem, which has two typical formulations, that is supervised and unsupervised ones. In a supervised formulation, the learner is given training pairs of samples, source target pairs, and this task can be solved using some common standard supervised methods. But in practice, it is common that we do not have paired samples. So there might be different reasons of it. For example, it is difficult to obtain pairs or something else. So the task should be solved using some unpaired, unsupervised techniques. In this case, the learner is given only unpaired, independent samples from the input and target distributions and needs to somehow estimate the translation map given only these independent samples. This unpaired, unsupervised formulation is much more challenging than the paired one because of the different issues. One of the issues is the ambiguity of possible translations. Indeed, there might exist multiple translation maps from the input to target domain, but not all of them are meaningful. That is, for example, on the top picture, we have the translation map, which is intuitively not good. It is bad because it does not keep the content and features of the input images. The bottom left picture is good because the content of the images are kept. So the learner has to somehow decide how to pick the optimal translation map, which, for example, keeps the content. The second issue, which appears in different domain translation problems and is crucial, for example, in image super resolution, is the problem of finding the translation map which keeps the content in the best way. That is, there might exist multiple translation maps which keep the content. But we need to choose the one which is the most, which keeps the content in the best way. That is, which translates the sample to the ones which are the most similar to the input. In our paper, we develop a novel neural network-based method to solve unpaired learning problems. And this method uses the theory of optimal transport, specifically incomplete transport, and provides a way to achieve the maximum similarity between translated and input samples. Of course, as you already know, it is not the first method for unpaired domain translation which uses optimal transport theory. It is which is based on optimal transport principles. For example, there was a recently developed so-called neural optimal transport method, which was successfully applied to the domain translation problem, unpaired domain translation, and also achieved results even better than some common GANs like cycle GAN and so on, and has some good features. For example, it naturally preserves the content of the input images to some extent because of the underlying principles of the OT problem. However, in some of the cases, it fails to preserve the content, and I give the examples on this slide. As you can see, some lady with brown hair comes the lady with the green hair, or the white bag becomes the black shoe, which is not okay in different tasks. So, it's just, so further I will explain the reasons why does it happen. The reason is that the neural optimal transport method is based on the classical optimal transport problem formulation. In this classical optimal transport problem, the goal is to transport the input distribution to the target one with the minimal effort. That is, to find some transport map T, which transports the distributions, minimizing the cost function C. For example, commonly used cost function is the quadratic one, which is written on the bottom of the slide. So it is a nice formulation which allows to keep the content generally, but in some cases when the distributions are unbalanced, they might lead to some failures, as we already saw. So in our paper, we propose another formulation called extremal domain translation, which allows to keep the similarity in the best way. So here we need to recall the notion of the support. By the support, we mean the small dimensional manifolds where the probability distribution Q lives, the real distribution. For example, the distribution of images. So it is a small dimensional manifold in the whole ambient space. And we want to find the points on this manifold, the images, for example, which are the most closest to the points of the support of the input distribution. It is some formulation which is visualized like on this right picture. So this formulation allows to achieve maximum similarity, but it is not obvious how to solve it in practice, because this objective on the supports, this restriction on the supports, is challenging to attain in practical scenarios. So we want to obtain another formulation to approximate the ET1. And we do it here. We consider the so-called incomplete transport problem. Informally, in this problem, we want to map the whole input distribution to the part of the target one. Formally, this could be written as a following problem, where the common equality constraint used in the optimal transport is replaced by the inequality one. So, what is interesting, this incomplete transport problem, it is also, by the way, the particular case of the widely used partial optimal transport, is this incomplete transport problem can be used as the interpolation between extremal transport and optimal transport. Indeed, If we consider the weight v equal to 1, we obtain the optimal transport formulation, and when we increase v and tend v to infinity, we get the extremal transport problem. So, what we can do, we can solve the incomplete transport problem for sufficiently large v, and the obtained incomplete transport maps could be used as the approximation of extremal transport ones. So, what we want to do? We want to solve the unpaired domain translation problem using this incomplete transport theory. So here we come to the so-called continuous incomplete transport problem. The learner needs to find the continuous incomplete transport mapping between two distributions using only empirical samples from these distributions. In this paper, in our paper, we propose a novel algorithm to do it with neural networks. As we prove in the paper, this problem can be solved using the following saddle point optimization objective. And when we solve this objective, the obtained incomplete transport maps could be used as domain translation ones. So this is the details about the algorithm. As you can see, it is a standard way to parameterize the potential and transport map as two neural networks, and then use the gradient descent-ascent algorithm. In our case, it is ascent-descent, when optimizing these neural networks. This algorithm was tested on different examples. For example, we started from the toy one, where we consider the first row, where we consider the mapping from Gaussian to the Wi-Fi, which is 3 arcs. This slide shows that our IT method allows to learn a mapping to the fraction of the output distribution. And this fraction is specified by the parameter v and the chosen cost function. So as you can see, we also conducted the not accept to accept experiment, and it works because our paper was accepted. Yes. So there are some details on our paper, on our algorithm. We use two neural networks, UNet and ResNet, some modified architecture in comparison with neural optimal transport standard quadratic cost, but we also experimented with other costs and yes, some other details. Here we present the examples of our method for the domain translation task. As you can see, varying the parameter v and increasing it, we may get more and more similar images to the target one. Here, when v is equal to 1, I should remind it, we get the neural optimal transport with strong costs. And as you can see, in some cases, it fails to preserve the content. For example, on the right image, we have this girl with black hair and the girl with green hair, the anime with green hair. And you can also see some failures on the left picture. But when the V increases, this issue disappears. So the green hair of anime girl becomes brown and so on. The same properties could be seen on other experiments which we conducted. And the question which may arise here is, okay, I will finish. Here I show that our method is not a gun, as you can see, because when we tend weight to the infinity for similarity loss, the learned maps tend to identity. Also some other examples. And the benefits of our approach. It is built on rigorous theory. It uses IT maps for generative mappings. It allows to use inequality constraint. in generative models, and it allows to control the similarity and pair translation task. That's all, thank you.
Okay, thank you very much, Elena. So maybe questions? Yes, where is the question? Yeah.
Yeah, thank you for your talk. I liked it really much. I was wondering if this optimal transport approach works for images really well. Do you think one of the variations of this optimal transport approaches can be used in natural language processing, for example, for translating one language to another or finding paraphrase detection or something like that? Have you tried something like that?
Thanks for your question. We considered different applications, but we do not tested our method on them. I just tested it on some real-world tasks. For example, on weather map super resolution. It is the project of the Skoltech. It's also like on images, but other neural optimal transport methods of my colleagues work in latent spaces, so I think the extremal transport could be also applied to latent space and somehow to natural language processing using this, maybe. It's just an open question now.
Okay, thank you. Okay, so I think we don't have time for questions. So, Len, thank you very much. So our next and last speaker for today, Gleb. Okay. Yes, I understood Gleb is also going to talk about optimal transport, but from another point of view, I expect. Okay. Yeah,
yes,
okay,
hello, dear colleagues. My name is Gleb Rozhakov, and I present a paper which was published in learing this year about the connection between the diffusion probabilistic model and optimal transport. So it's joint work with colleagues from Skoltech and Yandex. So, well, now everybody knows what is optimal transport. So we know if we have normal distribution with some mean and sigma, we can easily build optimal transport from this distribution to standard normal distribution. This is so-called montage optimal transport. So our main idea, our main result is that we numerically shows that this holds for DTPM models in multivariate domain. So if we take a rather complex multivariate distribution, build DTPM model for it, then we see that the full map will be optimal transport. What is DTPM? So in DTPM we have stochastic differential equation. We have deterministic part and probabilistic part. If we're interested only in the final distribution, but not only in trajectories, we can rewrite this equation as deterministic equation. But we need for this to know the distribution P. This distribution, namely the gradient of logarithm of this distribution, is named score, and we have special neural network for build this, for train this score and use it to solve this equation. But if we're interested not only in one trajectories, but in some distribution, we can move from one trajectory to the equation on the P, on the probabilistic distribution. So we came to Fokker-Planck equation finally. So if we consider only normal distributions, we see that the theorem about optimal transport holds true. So we have optimal transport, but the trajectories themselves are not straight lines. So optimal transport, we have optimal transport in general from time 0 to time 1. But it's not necessary that the intermediate trajectories will be straight lines. If we use another stochastic differential equations, and such papers are published, DTPM with another stochastic differential equations, we can get another trajectories which will be more straight, yet the quality will be better then. So our main numerical experiments, our main idea is that we take such multivariate distribution, exponential, and we show that the final cost is up to machine precision equal to the cost of optimal transport. Cost means sum of the distance between the initial point at time 0 and the end point and time t equal to 1 in our case, because we map to domain from 0 to 1. So to do this in multivariate case, we also use the technique called tensor train. So I have no time to explain what is tensor train, but the main idea is that we can split the diffusion and convection operators in such a way that we have to apply them sequentially. And the diffusion operators applied to the tensor train model is very simple. We can apply them to the chorus of the tensor trains separately. When we apply convection operators, we need to use another techniques such as TT cross and so on to make the TT decomposition of the probability on the next step. So why we think about optimal transport, why we, how do we find the connection between DTPM and optimal transport, we look at the various diffusion models which are built on the same initial point. So we take several neural networks that are generating images, dogs, cats, and so on. Take the same initial points when we make backward pass, and we can see that the pictures are rather have some similarity. For example, ears or where the animals looks have some similarities. So our big hypothesis is that if we take different images, for example, big image samples, from two different data sets, and we somehow can build optimal transport from one data set to another, then we can connect similar images with similar properties, color, and so on. So our main distribution, our main idea is that we numerically show that DTPM encoder, when we solve it using Fokker Planck equation in the TT format, make optimal transport up to machine precision. And this idea can be seen on real image datasets. Thank you. Any questions?
Okay, thank you very much. So questions? Yeah, okay.
Hello, thanks a lot for your presentation. It was very interesting. I have a question. Could you please tell a little bit of like sketch of the proof for normal distributions and that DTPM is the optimal transport map? So like I just remember more or less same or very similar results from papers like rectified flows, which says that if you have like if you try to train the map, the ODE or SDE between two distributions, and you train it on some pairs from one distribution and on second distribution, then the result says that the the transport cost between generated pair of starting sample and generated sample will be less than the optimal transport cost between the samples that you on which you train the model. And in this case, so like the question is, for normal distributions, do you mean that you should train the DPM with like a noise and transformed noise into a normal distribution, or with independent samples?
If you mean about two normal distributions, we have dependent sample sets, of course. So
with which?
We have dependent sample sets, but we do not have, actually we do not have proof for our hypothesis. Moreover, when our paper was under review on iClear, we put it on arXiv, and somehow other authors give us counterexample to the exponential model, where they have some parameter epsilon, very small parameter epsilon, and they said that optimal transport doesn't hold in our case, in the case with exponential. But we could not repeat numerical examples. So we have proved these results, unfortunately, yet.
So like, do I understand correctly that even if there are some results that states that this is not optimal transport, in a lot of cases, practically this almost is?
Yes, exactly.
Okay, thanks.
Thank you.
Okay, other questions? Yes.
Thanks for your presentation. Given the knowledge that DDPM performs neuro-optimal transport, do you think that one can utilize this knowledge in the direction of one-step generation? Like we know, the main limitation of diffusion models is their iterative denoising procedure, which makes generation quite costly compared to GANs, and there was a lot of work ongoing which does one-step generation, but usually with quality degradation. Some of them do some sort of rectified flow, like a recent InstaFlow, and probably neuro-optimal transport can somehow help this knowledge too.
Well, thank you for your question. I think that we cannot achieve one-step generation model because it's very hard. But for example, we can handle with less time steps if we have more straight trajectories. But I think these questions are the case of future work. I don't know the answers now.
Thanks.
Okay, and could you please go to slide with mixtures of distribution? So where K is uniformly sampled from.
Here?
Yeah, here. Yeah. But so what is PI here? So I didn't understand. So here we have. So P is. Okay, so it's two normal distributions, yes? Or okay, it's normal.
Sum of exponential distributions. So we transform by DPN model this distribution to normal distribution and by samples, and we empirically calculate the cost. The cost is the sum of distances between initial points and the end point. So these distributions are not the same. These trajectories are not the same, of course.
Yeah, okay.
Because optimal transport can be not unique.
But is it possible to go to beyond dimension 7 because here it's dimension like 2, 3, and 7. I mean,
yes, it's the case of our future work to extend these on images.
Okay, good. Thank you. So maybe other questions? Okay, if no, so Gleb, thank you very much. So let's speak Gleb and all speakers of today's sections. So now we have joint photo. So please, so let's stand here on the stage. А там уже оттуда пришли, да, люди? Это хорошо. Давайте все соберемся. А где у нас фотограф? Кто у нас будет фотографом? А, вы фотографы? Анна, ну вы хорошо выглядите. Да.
Вы, наверное,
с днем рождения.
Спасибо большое. Вы, наверное, в центр вставайте, и мы вокруг вас.
О чем мы сидим? Давайте по-быстренькому сфоткаемся, потом по-быстрому эти постеры и поедим снова. И выпьем уже наконец-то. Так, куда мы идем? Я буду командовать тогда. Ну, я где-нибудь потом встану. Вот. В центре должна быть перспективная молодежь. А мы где-нибудь сбоку. Ты перспективная молодежь?
В какой момент?
Так. Так, нам надо, чтобы кто-нибудь командовал построением. Даша, нам надо, чтобы понять, все ли влезают, потому что нас что-то много. Может, нам надо, чтобы кто-то в нижнем ряду выстроился, нет? Чтобы не все на сцене были. Все попадают, да? А может быть, кто-то тогда должен в первую часть, или так будет плохо? Да? Слушайте, а давайте кто-нибудь, вот те, кто еще поднимается на сцену, может быть, вы тогда вот сюда, вот как бы в нижнем рядом. Иначе мы как-то это... нет, это плохо будет? Нет, там просто во втором ряду... А? Вот я думаю, что вот если мы где-то вот здесь внизу встанем, то будет тоже неплохо, мне кажется. Ну, или плохо будет. Вот тут плохо будет? Так. А? Да, давайте спустимся. Я вот тут на лестнице, как всегда. А что вы не хотите фотографироваться? Анна, ну вам надо в центр, потому что вы в красном, ярком, и вы сразу как бы фокус. Да, конечно, как главный, Анна, как главный организатор.
Мне прям хочется, чтобы все присоединились.
Да, конечно, все. Мне особенно нравится все время, когда принесли большую камеру, то есть оно все фоткаются на телефон. Так, ну что, все готовы?
Мне кажется, да.
Давайте.
Да, все готовы? А вы нам скажете раз, два, три? Нет?
Чтобы все улыбались, надо что-нибудь сказать, там типа Feels Medal, или что-нибудь. Да. Так, ну что, нормально?
Главное, чтобы...
Ну потом они сделают там Super Resolution, Optimal Transport, и все будет нормально. Все, спасибо. А, да, мы идем на постерную сессию через 3-й этаж. Следуйте вот за девчонками, они знают, куда идти. А? Там постерная сессия будет. Ну, кто-то может через улицу пойти, кто знает, и у кого есть там куртка и пропуск, так будет проще, наверное. А все остальные вот через 3-й этаж следуйте. А потом мы возвращаемся сюда после постерной сессии, у нас будет, фуршет будет здесь. Кто не знает, то фуршет — это самая главная часть мероприятия. Всегда.